There it is.
Okay. Hi, everyone. Our speaker today is Daniel Massatt. He is a crucial instructor in the statistics department of University of Chicago. He got his PhD from University of Minnesota, and he worked with Dr. Luskin there, and he got his BS and MA degrees in applied mathematics from UCLA. Today, he will talk about electronics of relaxed bilayer 2D heterostructures in momentum space. Daniel, the space is yours.
I want to thank the organizers for the invitation. It's a pleasure to give the talk here. So as Fatma said, I did my PhD in Minnesota with Mitchell Luskin. So this is a continued work off of projects I was working with him before. In particular, we have a collaboration going on with Couxiris lab in the physics department at Harvard. So Stephen Carr used to be a graduate student with Couxiris. He's now a postdoc at Brown. And so this project was a joint work with him. Basically, we wanted to bring in the mathematics into a rather complex physical problem or physics problem in quantum theory. And so we wanted the physics on board to really make sure the physics was right and made sense and we were tackling the right problem. And then also bring in the math. So we really bring in the, deal with the complicated issues that were in play for this problem. So let me describe a little bit what the problem is. So there's materials called 2D materials, which are basically sheets of atoms that, and the sheets are only say one or a few atoms thick. There's a lot of different flavors, types of materials, depending on what type of atoms the lattices are composed of. There is graphene, which is made of carbon, boron nitride, which is more insulating, MOS2, and so on, with different electronic properties. And these can be actually fabricated in the lab, and is done frequently. And you can also stack them in different ways. So over here, this is a very famous image from Geim, showing the idea that you can just stack different materials on top of each other. And the advantage of that is that it will change the properties. So depending on how you stack them, the electronic properties change, which also means the possible applications change. So the idea is how, out of the different materials you have, how can you tune electronic properties? Now, there's one problem with this image is that he relates it to Legos and shows that if you stack all the materials on top of each other, they fit together like Legos. The problem is this doesn't really work in general because the materials have different lattice lengths. So they actually mismatch on top of each other in general. And further, you might actually be more interested in a mismatch setting. So for example, if you put two materials on top of each other, but you introduce a relative twist, you also break the periodicity. And this can actually generate something called a moire pattern. So you see there's sort of something that looks kind of repetitive here. It might not be exactly periodic, but it's sort of approximately periodic. And this changes the electronic properties a lot. So this is the real issue that we decided to tackle. It's called incommensurate materials. Incommensurate basically means they're aperiodic. So the periodicities of the two sheets aren't aligning. And my research has been particularly focused on the electronic properties of these materials. So we have some sort of Hamiltonian, say H, which is based off the Schrodinger equation. We'll be using a simpler tight binding model, which is commonly used in physics to study such large systems because the full Schrodinger equation is very complicated and expensive numerically. So simpler models are used. And we are interested in studying behaviors of the spectrum. In particular, there's different types of observables, for example, density of states or conductivity or Chern numbers and things like this that need to be computed. And so the goal of this project is to tackle how to compute these electronic properties in incommensurate materials. And we add a layer of complexity, which is introducing mechanical relaxation into the electronic model. So here I just show two rigid lattices on top of each other, but in fact, the atoms can move relative when they see each other. And when there's these large moire patterns, they tend to do that. So this introduces an even stronger complexity than just being incommensurate. So it makes it even more complicated. And that's where all the mathematical machinery comes in to build algorithms that can really tackle these types of problems. In the Geim picture, when you're actually periodic, there's a theory called block theory, which is basically just do a Fourier transform on the problem, and it reduces the whole problem to a unit cell. That doesn't work here because we don't have the periodicity. But we introduced two methodologies for tackling this problem that make it numerically tractable. The first one we did was configuration space, which is somehow parameterizing all of the sites in this infinite material over a compact manifold. And that works. But in this talk, I'm interested in talking about momentum space, which is actually in applicable materials, numerically much more efficient than configuration space, and introduces gives more physics intuition to it. It's very parallel to block theory. So block theory is very beautiful when you have periodicity. Here, if you use momentum space, you get you can use the effects of block theory, but there's some scattering that comes into play because of the incommensurate patterns. So that's what we're going to analyze in this talk. This is what the mechanical relaxation I was talking about looks like. So if we have an incommensurate material here, so here the Moire pattern is pretty large. The lattices look like this. But if you introduce mechanical relaxation, the sheet likes to locally become periodic. So here you see in this triangle, it looks periodic, and in this triangle, it looks periodic. But because the material is incommensurate, it can't just the whole thing become periodic. It only becomes locally. So it sort of forms local twists on all of these Moire patterns, and you get these sharp domain walls. So we need to introduce this into the model and then bring that into the electronics calculations, which I will do soon. The main plan will be to analyze 4 different spaces that are all equivalent for this problem and show that they can all be transformed from one to the other. So we get a commuting diagram between these 4 spaces. This here, where you just see all the sites interacting, you have this 2 infinite lattices coupling, is going to be called real space, the red one here. The configuration space is a clever way of mapping this problem onto a torus or onto 2 interacting tori. Momentum space is going to be the equivalent of block theory, but including all the complications that come from the incommensuration and the mechanical relaxation. And reciprocal space is going to basically be something very similar to momentum space, to real space, but the parallel for momentum space. So you'll see that the 2 blue, I'm color coding these, so the blue ones are the ones that correspond to a problem that's mapped onto a compact tori. And they are the 2 ones that correspond to good algorithms. The red ones are the ones that make more physical sense. For example, the real space here, you just see a bunch of lattices interacting, right? This makes more intuitive sense. But they're not good for algorithms because you have this infinite lattice that's not periodic. So, or 2 interacting lattices that are not periodic. So algorithmically, it's not efficient. The blue ones will be the efficient ones. Okay, so this is the outline. First, I'm going to introduce a lot of the notation in a very simple setting where there's just a single periodic sheet. No mechanical relaxation, no incommensuration, none of that. So this will kind of introduce some of our notations and the kind of objects we're looking for, the kind of electronic observables that we'd be interested in. Then I introduce what the model is that we're tackling. So I just define the real space model. We have these 2 interacting lattices, mechanical relaxation is included. So this will just define the problem we're looking for. The third thing I'll do is show what the 4 spaces are that I've been talking about and how they relate. And then I will start talking about the momentum space, which is the guy I'm really focused on here, and how the algorithm looks like and what its convergence behaves like. And finally, I'll show some numerical results. All right, so let's start with just a single monolayer. Forget the incommensurate for now, and forget the mechanical relaxation. So we're going to use something called a tight binding framework. And so what this corresponds to is if you have a lattice of atoms, or you have this periodic lattice that your system's defined over, in each unit cell, there will be a finite number of electronic orbitals. So these would roughly correspond to what we know in chemistry as like the s, the p, and so on orbitals. They're a little more complicated. They're derived using some DFT calculations with Wagner orbitals and all of this kind of thing. But the ending result is for each lattice site, we have a Bravais lattice in R2, a two-dimensional Bravais lattice. Each site will have a finite number of orbitals associated with it. So that builds our full degree of freedom space, which I will denote as omega. So it's lattice site across the orbitals. Orbitals will be a finite set. So then our matrix is defined over a discrete set. I define the matrix H. So R alpha is an element of our degree of freedom space. And that's just the lattice site and then the orbital. So if I have a vector over this degree of freedom space, the matrix acting on it is just going to be this infinite matrix times the vector. Because the Hamiltonian is periodic, you expect it to be a function of just the difference between the lattice sites and then also of what orbitals are interacting. Also typical for von Neumann orbitals is the assumption that the Hamiltonian is exponentially localized. So if you have two orbitals interacting that are far away from each other, the interaction exponentially decays. So the whole Hamiltonian is exponentially localized. All right, so this is the monolayer model. Now that's in real space. You can move this to momentum space by the block transform. So gamma star I'll denote as the unit cell of the reciprocal lattice. So it's basically the possible frequencies. And the block transform maps discrete L2. So this is just our wave functions in real space into L2 functions over the torus gamma star. So gamma star is the a unit cell that can be viewed as a torus, and you can have L2 function over it. Another way of thinking about this is if you have a discrete vector in L2, those are the Fourier modes of your L2 function over here on the torus. Excuse me. The block transform looks like this. So you can see that the psi r's are becoming the Fourier modes of this function over here. Okay. So finally, if you apply the block transform to H acting on psi, the H was basically a convolution with this little h, which was the function of the distance between the lattice sites. And the block transform acting on a convolution becomes the product of the block transforms. And so you just get this very simple formula. Now this little h for a single entry was a 2x2, or it was a matrix of just the orbitals cross the orbitals. And so now this is a very small matrix. And so we see that the block transform actually in the periodic setting really shrinks the Hamiltonian. So now it's just indexed by a wave number and you have a very small matrix. So what physicists will usually do is they study the eigenvalues because we're interested, when we're doing electronics, we're interested in the spectrum of the Hamiltonian. So now that we've separated the spectrum into small Hamiltonians indexed by the wave number here, we can just plot the eigenvalues. So that's the z-axis here as a function of the wave number, which is the x and y axis here. So this will be over this gamma star, all the possible q values, the wave number. Q is lives in gamma star. And you see something like this. This is in the case of graphene, so the carbon hexagonal two-dimensional lattice. You see that there's two little cones here. They're called Dirac points. So a lot of interesting physics tends to happen around here, around things like this. You can also have materials where you get more of a parabolic band. So it looks parabolic with maybe a small gap here. And a lot of the interesting physics happens at these points. This will be very important when we're talking about momentum space in general, because a lot of when we move a real space Hamiltonian with relaxation and an incommensurate system, a lot of in momentum space, all of the interesting things basically happen near these Dirac cones. So we get some sort of expansion around the Dirac cone. Or if it was a parabolic band, then it would be around the parabolic band. All right, so if we just write out this Hamiltonian completely in momentum space, you just sandwich the H with the block transform and the adjoint, and you just have this simpler function here. Now we're going to be able to do something similar in the incommensurate setting, but it's going to be much more complicated. Finally, we're actually interested in computing an observable. So an observable will be some trace of an object with the Hamiltonian. So it's basically looking at some, you look at the spectrum and its interaction on some observable. So it looks something like this. I'm going to focus on the density of states because it's the simplest observable, so it's easiest for presenting a talk. Our work certainly looks at more general observables, but this is the one we're going to focus on here. So roughly what it looks like is you could put a delta function or maybe an approximation to a delta function like a Gaussian. And you're acting on the Hamiltonian shifted by an energy E. And then you take the trace. So what this is doing is looking at the concentration of spectrum near E. And then you can scan over E to look at different energies. And you can see kind of the distribution of where your eigenvalues are in this infinite Hamiltonian. We define a thermodynamic limit of the trace. So it's basically just take a trace over a finite ball, normalize by the size of the ball, and then take the limit as the ball goes to infinity. And that gives us a trace of this infinite material. In the periodic setting, that's extremely easy because all of the sites look exactly the same because it's all periodic. And so this trace just looks like taking the matrix and only evaluating a trace element on the central single site. So let's say at the lattice site 0, and then summed over the orbitals. So if you want to look at a trace like this, just corresponds to this. So in this setting, we see that when we have this infinite trace here, which looks very messy to compute, because of the structure, we get a much simpler object here. One way of thinking about this is that all lattice sites are the same. So there's only one configuration that can happen. So you take a site, you see the same geometry everywhere. So that's the only guy you're interested in computing to understand the full trace. In the incommensurate system, all the sites don't look the same. However, you can parameterize the sites in a compact way, and that's going to be the key. So instead of having a single site here, you'd have an integral over a compact number of sites. Okay, so this is that density of states I was talking about. So right here, it was you have your Hamiltonian, you take a delta function centered at some energy E, and you take some sort of trace. It's giving you a weight to the spectrum of H near E. And then I said that you can plot that over E. So that's what this is. So here, this is near one of those Dirac cones I showed you in the previous image, say right here. That's the density here. You can see there's not many states here, it goes to 0. And then the states go more as you go away from the Dirac cone and peak kind of around here where there's this sort of flat region. And then you see that there's kind of a peak here in states here, and here it goes to 0. This is usually the interesting area right here. So that's what the density of states looks like. Here, you can also compute the density of states in momentum space. So this was the density of states for real space. We just projected G of H onto a single site. So G would be, say, your delta function centered in an energy. If you just sandwich this with the block transform and its adjoint, which is just the identity, because it's a unitary operation, you just get the block transform acting on these single sites, which is just the constant function. And then you just get this integral over the G acting on H. So this is a very small matrix, which makes this very easy to compute. You just have to integrate over more guys. All right. So that's the monolayer setting. That's introducing our tools. So we had, just to kind of review, we had a lattice and orbitals that gave us our degree of freedom space. We have our Hamiltonian H. We can describe the H by this small function here, which controls what the entire Hamiltonian looks like. It's exponentially localized. And then we can use a block transform to reduce the size of the problem. It's now integrated over a torus, and we have a very small matrix. And then we can compute an observation in either setting, either in the real space setting, where it looks like this, or in the momentum space, or the block after the block transform. And then we get a picture that looks like this.
Daniel, can I ask you a question?
Absolutely.
Yeah, how do you compute these things? Like, do you discretize it and you get matrices, or you using Fourier transforms? Can you just talk a little bit about that?
Yeah, so here, this guy would be computed just using a discretization of this integral. This Hamiltonian is very small. It's, for example, for graphene, there's only 2 bands. It's just a 2x2 matrix. So easy to solve the spectrum. And for this guy. For the bigger problem, it's going to be harder, but yeah.
Okay, yeah, thanks.
Oh, actually, for the real space, though, if you want to compute this guy, you truncate this matrix centered at the site that you're projecting onto, and you make that truncation radius quite large. The larger it is, the more accurate the spectrum will look like. So here you actually need very large matrices. Over here, you need very small matrices, which is actually a big difference between configuration space and momentum space. That exact same idea that you see here in this simple setting shows up in that harder setting.
Yeah, that's what I was getting at. So, I mean,
Yeah.
when it comes, so in your problem, are you going to avoid this large computations or you're going to tackle them? So that's what.
So what happens is in the configuration space, you get these very large matrices, and you have to analyze convergence rate based off of the level of resolution you want of your spectrum. So the finer details you want here, the larger H has to be. So we have an analysis for that for the configuration space. The momentum space, here in the monolayer, you see that the matrix is very small, which is very helpful. Once you introduce relaxation and the fact that the system's incommensurate, it's still, the matrix is decently small, but it's much larger than it is in this setting. And so there's kind of an analysis for the rate of what size matrix you should expect based off of the system you're looking at.
Okay, thank you.
Thankfully, in that setting, you still can do diagonalization in general. In the configuration space, you usually use Chebyshev polynomials to approximate this function G, because the actual spectral solve is too hard.
Thanks.
Yep. So in the bilayer setting, then we have two of these sheets. So I'm just going to index the sheet by J. The total degree of freedom space is the union of the two degrees of freedom sets for the two lattices. And then the Hamiltonian will just be mapping discrete L2 to discrete L2. So it's the same sort of setting as before, but now there's two sheets. And the matrix is still going to be indexed by the orbitals, and then also by the interaction between the two lattice sites. This is without mechanical relaxation for now. And then we have the exponential decay of the coupling functions. Now, if you'll notice, before we talked about when you're doing interaction inside the layer, it's just there's discrete number of values that the H can take because R minus R prime live in the same lattice. Now we're in the incommensurate setting, R and R prime live on different lattices that aren't commensurate with each other. They're aperiodic. So this can actually take any value in R2 now, the interlayer coupling between the layers. We're assuming the system is incommensurate, meaning they're not periodic with each other. These two lattices are not periodic, which can be summarized by this condition here. So just make sure the lattices are very different. It's the lattices are incommensurate and also the reciprocal lattices. So the reciprocal lattices is just the same lattice set when they dot together, then it always becomes a 2 pi times an integer. Okay, so let's talk about configuration a little bit. So this is where the first torus comes in. So if I look at a random lattice site, like let's say the blue from sheet 1, I realize I can actually parameterize it by the unit cell of the opposite sheet by just looking at where it is in the unit cell below. So just project it down into the other sheet, modulate, and just see where it lives in that lattice. This vector B is unique for each lattice site, and it completely represents the local geometry of that site. So this vector B will be the key guy, and this is going to be on a torus because this is now just a unit cell. You can consider it periodically wrapped. So gamma 1 and gamma 2 will be the unit cells for sheet 1 and sheet 2. And if we want to include mechanical relaxation, what you can do is actually just look at, you can define a function that's periodic over each of the tori. So this is going to be the relaxation for lattice sites of sheet 1. You can make them as a function that's periodic over the opposite unit cell. And what that means is if you want to see how a lattice site moves, let's say it starts at site R on sheet J, it will simply move to R plus UJR. So R here will get modulated since this is a periodic function with the opposite periodicity. And then it will give you a displacement vector for how the site moves. So this is sort of a mapping that shows the displacement fields as a function of the configuration. If you apply that to a bunch of lattice sites, this is the kind of pattern you'll get. The image is exaggerated, so it's easier to see. Relaxation takes longer than this, than you see here. But this is the kind of idea you get. You get these large triangular patterns, which, by the way, you can see in experiments when you're doing bilayer twisted materials. You can see these triangular patterns. Now the Hamiltonian in the tight binding model changes like this. You get interaction between lattice sites, and now it's a function of the orbitals, but it's the distance between the new sites. So we're going to have r plus the displacement of r minus r prime minus the displacement of r prime. And so now intralayer and interlayer is going to start seeing this incommensurate pattern. The other periodicity is going to show up in all the interactions. So this Hamiltonian is a little more complicated to analyze. So to do that, we kind of want to rewrite the Hamiltonian in terms of configuration. So to do that, we take the real space Hamiltonian. We just write it down what it is. And now what we do is, here I'm looking at the intralayer, so it's within the same sheet. So I have r plus uj. So I basically just move some guys around, and I want to rewrite this as a function of r minus r prime and the configuration of r. Because the idea is then my Hamiltonian is written in such a way that I have the starting position, the configuration, and then the distance between the sites, and that gives me the whole Hamiltonian. So the idea is rewrite the Hamiltonian in terms of lattice site and local geometry. So I kind of relocalize it into the torus. So that's what's happening here. BR is just the modulation of R. So that maps immediately because uj is a periodic function with the opposite periodicity of R, the opposite sheet's periodicity. And I get configuration, distance between the sites. So this gives me the intralayer interaction in terms of configuration. Interaction between sheets is somewhat similar. So because site R has the opposite periodicity of U2, R prime has the same periodicity. So it makes no difference just to plug in an R prime here. Same here, if I have R prime here, I can just throw in an R because it has the same periodicity as U1, so it doesn't change anything. And I get the whole interlayer coupling is just a function of the distance between the sites, which is what I had before. I had the coupling function is just written as the distance between the sites and then the orbitals. So this takes these large infinite Hamiltonians and rewrites them as local interactions, just either the distance between the sites or a distance between the sites plus the configuration included. And now what I'm going to do is rewrite this whole Hamiltonian in terms of this configuration. Okay, so basically we now are going to have two tori, so gamma 2, gamma 1. That's going to become our new degree of freedom space as functions over the torus. So instead of having these infinite lattices, I'm now just going to have functions over tori. When I want to show coupling between different sites, this is now going to be done by translation operators. They're going to couple one configuration to another because every site has a configuration. If I want to talk about the coupling between them, it's done through translation operators. And there's this random sign swap. That's just a technicality about how configurations couple. And so what I end up getting is a new Hamiltonian called H configuration, which is a combination of translation operators and product functions, multiplication operators. And the idea is this is really just corresponding to the exact same thing. Whenever I have a translation operator, that's corresponding to a hopping, say from R prime to R or in the interlayer coupling. So that's conducted by the translations, and then the functions correspond to these H's here with the function of the configuration. So there's going to be H of R's, which can be written in terms of that guy I just showed, and interlayer couplings also. So everything becomes translation and multiplication operators over the torus. And here's a kind of a picture version of that. We originally had two lattices. Say you have site R2 here, and maybe an R1 and R1 prime down here. Everybody's interacting, but if I move it to the torus setting, it's basically points on the torus interacting with each other. So you kind of locally see a lattice. Each of these sites over here corresponds to somewhere on the torus. The torus is just the unit cells of the sheets. And these guys will be coupling with each other through these translation operators. And you can define a mapping, which I'll call script R, which basically takes the Hamiltonian and writes out this version in terms of the coupling functions for this guy. So you have the coupling functions over here, and you can just expand out the matrix based off those coupling functions like this. So as long as you know these HRs and this interlayer coupling here, you get the whole matrix here. So there's a mapping from this torus over to these guys interacting. All right. So I know it's a little confusing in a way, but it's kind of necessary for the algorithm because now we have something that's compact. So over here, all the sites were just scattered across this infinite plane. Very hard for a numerical algorithm to be tractable. Now we have the Hamiltonian kind of expanded locally around all the configurations, and you just compactify that. So when you get down to an algorithm, it'll involve an integral over the torus and then a matrix, using a matrix locally defined. I'm not going to focus on that space too much. I'm more interested in momentum space, which will look kind of similar. But I need to move from that setting I just talked about over to momentum space or frequencies. And that's done through this block transform. So I'm going to, just like before, I talked about the block transform. Now I'm going to have a block transform per sheet. That's going to be described as GJ. G is going to be the, since we're acting on the product of the two L2 spaces, the G is going to be the composition of the two of these. G1 acting on sheet 1, G2 acting on sheet 2. So it's just the block transform for sheet 1, block transform for sheet 2. And it turns out that if I transform real space, I'm going to get a very similar Hamiltonian to before, except now instead of having translations with respect to the lattices, it's translations with respect to reciprocal lattices. And I have functions of the wave numbers instead of the, which is over the reciprocal lattice unit cells, or the Brion zones, they're also called. And we have the multiplication operators over those. So we have two different tori, the gamma 1 star and the gamma 2 star. So this is just to emphasize how similar the structures are. You got translations, and then translations, interlayer coupling, multiplication functions, and translations. So it's all very similar. This is just showing how you can actually derive these H tildes, the momentum space couplings, directly from the real space. There's actually some very simple formulas. One's a Fourier transform, not surprising since we're moving to frequency space. And the other is just it's a manipulation of these periodic functions here. Kind of swaps the order of the periodicity. But we don't need to go over that too deep closely. We got to pick our battles. Skip that. All right. So it turns out, so we have four spaces. We have real space, which I talked about, configuration space, which is over the torus. We have momentum space, which is also over a torus, and it has a corresponding extension to becoming two lattices interacting. That's called reciprocal space. So it looks, it's just defined over the reciprocal lattices now and the orbitals. So it looks very similar to before. And then what we can do is actually define a commuting diagram that maps all of these Hamiltonians to each other, kind of showing an equivalence between them all. So I talked about the script R, where you kind of unfold this torus into the full real space. The block transform moves you to momentum space. There is a similar unfolding, script R star, which moves you to reciprocal space. And then you can do block transform again, because the frequencies for the reciprocal lattices is just the original unit cells. So you can do a block transform the other direction, and you map all of the four spaces together. All right, that might seem like a lot of machinery going on. The point is these two blue guys are where good algorithms come from. The two red ones make more physical sense, but if we want to actually compute them, then we need these more complicated objects. And in particular, the momentum space formulations can be kind of hard to derive. So we really needed a rigorous structure of how to build this Hamiltonian here and how to build all the coupling. And here's a picture version. So we have configuration space here. So we have this Hamiltonian defined over the two tori, where you see translation operators are coupling configurations, unfolded into lattices in real space, block transform again to being defined as translations over tori. This is momentum space. And then unfold again. All right. And here a result that we have. So we're interested in computing observables. I'll again focus on the density of states. So we have a thermodynamic limit of the trace of the real space, let's say. It turns out that all four of these spaces, observables will be the exact same in any of these spaces. So if I take the trace in real space, it's the same as the trace over the tori. So that'll be like an L2 trace. This is an infinite lattice again, so it'll be a thermodynamic limit like this. And then this will be an L2 trace again. So if we assume G is analytic and over the spectrum or in a neighborhood of the spectrum, then all the traces correspond. All right. So our goal is to build algorithms. So we're going to try and focus on this blue one here, the momentum space trace algorithm. And we're going to find that's much more efficient for certain materials. Okay, so the whole point was we bring it to a torus because then the whole Hamiltonian is described locally based off of each element of the torus, and then we can just integrate over a compact set. So the first thing we want to do is expand the matrix locally around a Q. So a Q is an element of the torus. It's a wave number. So we build a matrix. We expand it over the reciprocal lattices. We can build that matrix in terms of a coupling centered at a shift Q. And if we actually write out the trace, what we see is the trace looks something like this. So it's an integral, the sum over the sheets, integrals over the tori, and then it's just G, our function of interest. Oh, sorry, there should be a G right here. I apologize. It's a trace of G of H. Then we have the G acting on this Q matrix, and we project onto a central site. Okay, so we have a wave number of interest. We expand locally into a large matrix, or small, depending on what we want. And we're going to evaluate G at H and then project onto the central site. And then integrate over all the sites. So we've kind of parameterized all of the sites in this infinite matrix and made something more compact. So to make that numerical, all we have to do is truncate this Q of this Q. So this locally expanded matrix is technically still infinite, but we're only interested in the projection on the center of the matrix. If you think of the matrix as like an infinite circle, then we're just interested in projecting on the center. So we want to truncate in a smart way. In configuration space or real space, when you do something like this, the matrix still needs to be very large because of the resolution. In momentum space, there's a nice structure to your Hamiltonian, which really saves you a lot of computation. So we'll take a look at that real quick. Okay, so when you're expanding in momentum space, before you introduced relaxation or the incommensuration, each wave number corresponded to a simple block theory problem for a single sheet. So let's say we look at these Dirac cones. Then each wave number has corresponding energies. And what you see is near the region of interest, the energies are all close. But as the wave number gets larger, the energies get higher. And so what you kind of expect is wave numbers that correspond to high energies won't contribute much to electronics happening near the region of interest. And so this is where the truncation comes into play. So to deal with that, we take off some cutoff in energy around the region of interest. We could see what wave numbers correspond to those energies of interest. Then to make something numerical, we add a buffer region. So this is this dark region in this momentum. So this is telling us what wave numbers we expect to contribute to the problem. Now, the matrix with the lattices, each lattice site had a corresponding wave number. So we just highlight, this is the two infinite reciprocal lattices interacting. We expand out these regions. So we just color these regions, these reciprocal lattices, if they correspond to these regions of interest. And we see they form isolated little circles. And so for numerics, the coupling between these circles is minimal. So what we can approximately do is only keep one of these regions and then compute the numerics there for that wave number. And then we'll integrate over wave numbers, but each one will still have a small matrix, larger than in the block theory I talked about before, but still much smaller than you would in a different setting like real space or configuration space. All right, so let me jump over here real quick. So what happens is when you expand out this Hamiltonian, you truncate like that. So you get some sort of circular cutout. You'll find that the convergence is actually very strong because as you go in, if you expand around a region of interest, let's say we're interested in this region, these areas have a higher energy, so to speak. Let me jump to this slide. So this is the Dirac cone, that area of interest. This is the expansion in lattice sites near this Dirac cone. Let's say we're interested in the energy region here in red. I'm going to call QJJ just the parts that's coming only from monolayer interaction, so as if there was no relaxation or incommensuration. Then you can see all of the effects from relaxation, say this delta Q11, for example, or all the interlayer couplings these guys. These are the interactions between these different rings. Then what we see is that actually the Q2, as you go higher up these rings, the Q22 to Q33, they correspond to higher energies, and they're going to contribute more, they contribute weakly to what's happening here. So you can actually show a very fast convergence rate in the truncation of the matrix in this little r here, the size of these cells. And so what we do is we do we have a convergence theorem for this. So if we truncate with this little r, we actually get exponential decay in our choice of r. So the larger r is, the faster the system converges. This is our algorithm, and then this is the trace of the guy we're looking for. And this is the term corresponding to the resolution. So normally what happens is in a more real space setting, then this convergence is very slow. The convergence rate will depend on the resolution. Here in momentum space, you don't have any resolution element. In the exponential, all the resolution shows up here. So it's more of a logarithmic scaling with the resolution. Over here, this is what's interesting here is that in momentum space, the coupling gets longer range when you have sharp moire patterns. So when these moire cells are very large in momentum space, the frequency coupling is much higher. And that's because there's these kind of sharp frequency effects to these boundaries. All right. And so finally, we just have some numerical results. So we have kind of convergence rates. This gamma parameter can change with respect to the angle. So as you get to really small angles, when you have two materials twisted, the moire patterns get very large. You can analyze the convergence rate based off of the angle. You can also look at truncation. So if you truncate the coupling functions, how that behaves with data. And then the last thing I wanted to mention here is you can also, since the matrices are very small, you can look at all the eigenvalues and plot them as a function of your Q. And so that makes something called band structure, kind of like the picture I showed before. This is over a line cut, like a high symmetry line cut. So this becomes very interesting for physicists as well, because they're always interested in band structures and understanding, kind of looking at the spectrum in terms of the wave numbers. So that's another advantage of this momentum space type structure, is that you can actually get a lot of physics just out of what the Hamiltonian looks like, along with the computational efficiency. Also, we did a project where we took the same system, but without the mechanical relaxation, we computed some conductivity and density of states. So we have some convergence results. We show the convergence is very fast relative to the configuration space algorithms. And then we also get some quick computations of conductivity, which is a pretty hard observable to get normally. But momentum space is efficient enough that since you can solve for actually diagonalize everything, it works. All right, so that's what I've got. Thanks for your attention. Yep.
Thank you very much, Daniel. Any questions?
Yeah, maybe I can ask one.
Go ahead.
So your theorem had an error bound, it was an absolute error bound, right? So can you convert this into a relative? Like, can you say anything about the relative accuracy?
Oh, the relative accuracy? Yeah, so usually the actual values that are observable are very reasonable numbers. There's nothing very interesting about them. So they'd be just order 01. So the convergence will look the same.
Okay.
So yeah, so that's a good question. That's why we just
Any other question? Sorry. Any other question?